The steps to solve a polynomial inequality are 1. Write the expression on the left side of the inequality. 2. Find the zeros. 3. Use the zeros as boundary points to separate a number line into intervals. And then 4. Pick test points in each interval. Intervals that are true are part of the solution. For example, let's solve this polynomial inequality. The first thing we want to do is set the right side equal to 0. So we'll subtract x squared on both sides. And now we want to find the zeros. So let's set this equal to 0 and factor. We can factor out a GCF of x squared, and then set each of those factors equal to 0, and solve. The equation on the left, we take the square root of both sides, and we get x equals 0. And then on the right, we add 1 to both sides, and then take the square root of both sides. X is equal to plus or minus 1. So these values for x we will call boundary points. And we're going to put them on a number line. So we have -1, 0, and +1. Notice that in this example, the boundary points break up the number line into 4 separate intervals. We want to choose a test point in each interval and test it in the original inequality and see if it's a true or a false statement. We're looking for the true intervals. So in the first interval on the left, we'll choose, say, -2. So let's test -2. And we'll test it in the original inequality. And we're asking, is this a true statement? -2 to the 4th power is 16, and that is indeed bigger than 4. So this interval is good. It was a true interval. Next, we'll test a point in the second interval. Let's say we test -1/2. And again, we'll go back to the original inequality to test -1/2 to the 4th. We're asking, is that greater than or equal to -1/2 squared? -1/2 to the 4th power is 1/16. And -1/2 squared is 1/4. This is a false statement, so we do not want that interval. That one's false. Next, we can test a point in the third interval. Let's say we test +1/2. Going back to the original inequality, we'll plug in 1/2. We're asking, is this a true statement? We get 1/16 is greater than or equal to 1/4, which again is false. And finally, we'll test a number in the fourth interval. For example, we can test 2. So we have 2 to the 4th. We're asking, is that greater than or equal to 2 squared? 16 is greater than or equal to 4. That's a true statement, so we're going to make a mental note that that interval is good. So the solution to this polynomial inequality are those 2 intervals that are true. The first interval is -∞ up to -1. And notice that we have equality, so we can bracket that -1. Then we'll union that with the other true interval, 1 to infinity. And again, we can include the 1 due to the equality. In our next example, we have another polynomial inequality. We'll start by subtracting 3x on both sides so that we can make the right side 0. Our next goal is to find the x-intercepts, or zeros. To do that, we will set this equal to 0 and factor. So there's a GCF of x. We'll factor out an x. And this time we're setting it equal to 0. We can now factor the quadratic. We have two numbers that multiply to -3 and add to 2 are 3 and -1. From here we just set each of those factors equal to 0 and solve these equations independently. X is 0, x is -3, and x is 1. These values, these zeros, or x-intercepts, we will call boundary points. And we put those on a number line. -3, 0, and 1. Make sure you put them in chronological order. Notice again in this case, those boundary points break up the number line into 4 separate intervals. We need to now test a point in each interval into the inequality and see if it's true or false. Up first, we can test a point in this first interval. Let's say we test -4. -4 cubed plus 2 times -4 squared. We're asking, is that greater than 3 times -4? Here we get -32 is greater than -12. That is a false statement, so we do not want to keep that second interval. Make a note that that one is false. Next, we'll test a point in this second interval. Any point you want. I'm going to choose -1. Again, going back to the original inequality, we have -1 cubed plus 2 times -1 squared. We're asking, is that greater than 3 times -1? Here we get 1 is greater than -3. That is a true statement. Make a note that that interval is good. Up next, we need a number between 0 and 1. So let's test 1/2. 1/2 cubed plus 2 times 1/2 squared. Is that greater than 3 times 1/2? Here we get 0.625, or 5/8, is greater than 1.5, or 3/2. In this case, this is a false statement, so we don't want that interval. And finally, we will test something bigger than 1. Let's test 2. 2 cubed plus 2 times 2 squared. Is that greater than 3 times 2? Here we get 16 is greater than 6, which is a true statement. So we want to keep that fourth interval. Again, the solution are the intervals that are true. So this first interval, -3 to 0. And notice the original inequality is strictly greater than. We do not have equal to. That means we cannot include these x-intercepts. So we'll leave those as parentheses. -3 to 0. Then we'll union that with the fourth interval, which was true, 1 to infinity.